Good morning. It's 10:05. Let's make a start. Can you guys at the back hear me? Great. My name is Jianzhong Qi. If you have been to this lecture, like in the first lecture of the semester, you might see me appear for a brief moment of a few seconds. I'm one of the lecturers for the subject. For this week, I'm going to cover the lecture. So what do we do in this lecture? So at the end of the last lecture, Shannon already introduced a little bit about strings, and he also motivated the content a little bit, talking about pattern search. And continuing on that, in today's lecture, we're just going to build on top of that, and we're going to talk about string search. So if you have done a bit of biomatics, if you've done a little bit of bio, you probably know that a DNA is a sequence of a lot of characters, and in particular, typically there's 4 different characters that can appear in this long sequence, ATCG, right? And if you want to search and you want to look for a particular gene inside of a really long sequence of DNA, it's what we call a pattern search. A gene is just a small piece of ATCG pattern, and the DNA is our search target, a long sequence, millions of ATCG characters. Now, similar problems appears not just in DNA search, but also in our day-to-day kind of interaction with the internet. If you go to Google search, you search for apple and banana. That's again a pattern search. Your pattern is apple and banana, and the target will be the entire internet. And by the entire internet, I mean all the web pages on the internet. And every web page, in the end, you can think of it as a sequence of characters. Obviously, there's also some video and multimedia contents, but let's not worry about that. So it's all about this searching problem. But all right, we established that from an application level, it's an important problem. But why makes it academically interesting? Where's the challenge? Let's think about this. So here, this top sequence in here is our target string, a long sequence of ATCG characters. And here, ATG is our pattern. So why does it make an interesting problem? Now, think of this long sequence of ATCG as a sequence of integers. And also think of this ATG as a single integer. Then the problem falls back to what you have learned in the last lecture, right? You have a long sequence, an array of integers, and you want to find whether a particular integer appears in that long array or not. And you guys know how to do it. How do you find an integer within a long sequence of integers? Yeah?
You start at the beginning,
yeah.
check if the first one is the integer, if it's not, keep going in linear search.
Yeah, linear search, perfect. So Shannon did his job. Now, easy, you do that. And we can actually make it a bit faster if we can modify this sequence a little bit, right? How do we modify it? The white page kind of thing? Yeah, you sort it, right? If it's sorted, you can do binary search. Very good. And that reduces the time complexity from O(n) to O log n. Now, there's just 2 issues with this process. When you processing strings instead of integers, 2 issues. First issue is that you can't really sort it. It's a DNA sequence. If you sort it, it breaks the pattern, right? Then it's not a DNA sequence anymore, or at least it's not the target sequence that we are talking about. So you can't sort it. So at least the O(n) time complexity must stay in there. We can't do much better. The other issue is that the pattern string ATG here is not really an integer. If you want to compare the first element, first letter or first character of the DNA sequence with this pattern string, it's not a one-off cost. Not like integers. You compare the first integer in the linear sequence with your pattern number. If you don't match, you move on, right? That's a one-off comparison cost. But for this string comparison kind of thing, pattern comparison kind of thing, you can't just compare the first letter and you say if they match, they match. If they don't match, the whole thing doesn't match. It's not like that. If the first character in here, A and A matches, you have to move on to the second one and compare whether they match or not. In here, in this particular example, they don't match. We move on to the second, starting from the second character in here. Again, we compare with the whole pattern string and repeat the whole process. So each time when you start from a particular position in this target string, it's not an O1 cost. And that makes this problem a challenging problem. And obviously, we start from an easy solution for a challenging problem. And the easy solution is pretty much like visualizing here. We just go through every element, essentially a linear search, go through every starting position of the target string. By the way, this longer one, we call it target string for this class context. And this shorter one that we want to search from the target string, we call it a pattern string. Now, the solution would be starting from the first position of the target string, let's cut a piece of the target string that is as long as the pattern string. They must be of the same length such that they can match. If not the same length, they can't match anyway. So cut the same piece, 3 letters in here, same length as the pattern string, compare them, do they match or not? In this case, don't. Move on to the second position of the target string, compare them, do they match? Third character, and again, a 3-letter kind of subsequence, compare with the pattern string, do they match, and so on and so forth. So we just keep going until we finish the whole thing. Here, let's go for a sort of a longer kind of example. Suppose our target string is Mary, Mary, marry me, right? This is target string with 19 letters. I have a pattern string mark with 4 characters. Let's try to find mark within this long sequence, and let's see whether we find it or not. Following the procedure that we just described, what we will do is that we're going to compare the pattern string mark with the target string starting from the first position. And to track this comparison, we need to use 2 looping variables, right? Just like when you do linear search, you have to use a linear looping variable, for example, I, to help you loop through the first element up to the last element. So starting from i's element, I being 0, up to the end. So we need to have a looping variable. In this case, I'm going to use a s to represent my looping variable to go through the target string. And I'm going to keep using this s for the rest of the lecture. So s is a looping variable, right? Similarly, I have a I as a looping variable. Now, this I looping variable is to go through every character in the pattern string and see whether we can find a match from between the pattern string and the target string. So at the beginning, we're going to try to match the subsequence of the target string from the S position, which is S being 0, so first 4 letters. And we also start from the pattern string first letter, and I also being 0. And the comparison would be just is the S plus I's letter, in this case S and I, they're both 0, is this letter equals to the I's letter of the pattern string? T is the target string, pattern, P stands for the pattern string. So that's just the idea. So make that comparison. In this case, they match each other. Then I'm going to try to match the second one. So to match the second one, we'll just do I++, such that we can do like, then once we do I++, now I will become 1, and S plus I becomes also 1 as well. In this process, S stay the same, we only change I. So starting from each position of S, keep increasing I until you find a letter that don't match. In this case, the second letter, they don't match already, and we can just pretty much just move on. And we'll try to match this mark with Airy. So S got this time, this is the moment where S got increased by 1, and I got reset back to the leading character of the pattern string. That's the linear search process. So in this process, how many iterations do we need for the S variable such that it hits the end? Suppose that we have n letters in the target string. So the length of this, suppose the length of this, here the length is 20, and let 20 be a symbol n. So how many iterations do we need to exhaustively search the whole sequence? Anyone? N times S?
S being the length of the one we're looking.
Yeah, S being the length of the, you mean S being the length of this mark? Or are you talking about the target string? So suppose the target string has n letters, and to exhaustively go through them, let's not worry about the pattern string yet. Just talk about the target string. To exhaustively go through it once. N, exactly, N. We can actually do a little bit better than N, because now, if you think about it,
N minus the length of the string minus 1.
Very good. So at this moment, we are S is at the position of n minus m, exactly, strictly speaking, it's n minus m minus 1 because we started counting from 0, but don't worry about it. Let's just simplify that. And this is a point where we say, if this last bit of sequence don't match the pattern string, there's no point we keep going. And the reason for that is, well, we don't have enough characters left there to match with the pattern string, right? So the maximum we need to go to is just n minus m. But the actual complexity is not just O(n) though, because as we just described, every time when you look at one position, one iteration of this target string, we need to compare with the whole pattern string. Well, in the worst case, compare it with the whole pattern string. And the whole pattern string, suppose it has a length of m. Then what would be the overall time complexity then? N times m, right? You multiply the two. And I'll give you a particular example why it has to be like that. Now here, look at the second example. We compare with AAA with AAAB, that's for comparison, right? They don't match. We have to move up a little bit. Again, we compare this second AAA with AAB. And we have to compare the whole 4 letters to see that they actually don't match, right? Because the first 3 letters, they all match. And repeating this process, again, they don't match. We again shift up. And that's another 4-letter comparison. And if you keep going and keep doing this, there's another 4-character comparison. So for every 4-character substring of the target string, we need to do a 4-character comparison with the pattern string. And 4 here being the length of the pattern string, m. Yes?
Is there a way to skip that? Because, like, in this example, right, where you're going so the first 3 match, and then the final one doesn't match.
Yeah.
Shouldn't you be able to, like, currently the algorithm would just go to the next, which is row 4, column 4, sorry, would just go to the next one along. But shouldn't we actually know that column 4 can't be correct because, like, based off of the check we've already done, it can't have the right characters, so we should skip all the way to column 7.
Great observation. That's what we're going to cover next. Maybe we can switch the position and you come here and talk to us how to do it. Very good, great observation and then great notice. So let's complete the complexity analysis first, and then we'll get to that very soon, right? So time complexity per se is O n m. Technically, it's n minus m and then times m, but we can simplify them a little bit, assuming that the m is typically smaller than n. So we don't worry about the m squared bit, just n times m. And the question is, can we do O(n)? And to achieve O(n), we do need to do a bit of skipping. But how do we skip? And to achieve that skipping, let's look at our solution called the KMP algorithm, named after famous computer scientists Donald Knuth and Morris and Pratt. KMP algorithm. And Donald Knuth, by the way, is a Turing Award winner. And Shannon introduced Alan Turing in his last lecture. And in the computer science discipline, the top award, we don't have a Nobel Prize, unfortunately. The top award that any computer scientist can win is what we call the Turing Award, named after Alan Turing. Well, technically, last year's Nobel Prize actually goes to a few computer scientists, but not for their contribution to computer science, their contribution to neural networks, which is still computer science, right? Artificial intelligence. Anyway, so let's look at how this KMP algorithm helps us to achieve actually a linear time pattern search. Before we start that, so far so good? Am I going too fast, too slow, too boring? I understand that. I probably won't be as funny as Shannon can ever. I can't ever be as funny as Shannon, but I'll try my best to be at least as informative, right? So how does the KMP algorithm work? Key idea of it is when there's a mismatch, we don't restart all over from the beginning, but we're trying to skip forward a little bit. The idea being, so now let's change the target string a little bit for argument's sake. Now I have to change the string such that the example stands out. So that's the reason why we suddenly change a different target string. So now our new target string says she, and there's a star sign, and then s. There's a little bit further, but let's not worry about that yet. So I have hide something such that it helps us illustrate the idea in the later step. We start from the simple one. Now, and our pattern string is she shouts. Makes no sense. It's just a random pattern that will help us illustrate the algorithm. So we start with the simple idea that we just follow, right? Start from the first position, and let's try to match it with the pattern string. And I starting from 0, not 5 in here. Starting from 0, and apparently they match. Because they match, we follow the previous steps. We say, all right, let's move I to here, compare whether they match or not, and still match. Let's keep going, and match, and keep going, and match, and keep going. Oops, they don't match. This is the point where they don't match. Now, ideally, because we say that we don't want to restart again, so ideally, here's what I'm going to do.
Why don't they match?
Oh, actually, this match. Sorry, this 2s match. This is the moment 1, 0, 1. So I being 5. This is the moment when they don't match. All right. Now, ideally, what I will do now is that I'm just going to keep moving here, because none of these match. So I'll just skip. Right. That's the ideal case. But we can't do that, because if you look at this bit, the green bit and the red bit, they actually match. So there's a bit of risk that happen to be, this is H, this is E, this is star, this is S, this is H, this is E, L, L, S. If that's the case, we are screwed, because then we miss a match. We can't really do that. So when there's a mismatch, we can't just skip everything that we have compared so far. We're trying to jump, but we can't jump from here to the end of the lecture theater to the entirely the other side. We have to meet in the middle way. So where is the middle way? We want to jump forward and then fall back a little bit. And that fall back, we call it a delta. So what's the delta in this case? 1, right? 1, because the red bit matches the green bit, and the length of this matched bit has a letter of 1, so we fall back by 1. And this is the idea. If there's a mismatch, let's jump from S to S plus I being the length of the matching so far. So jump the whole way forward. So I'll jump the whole way forward. This is my mismatch point. But I have to fall back a little bit, and this fallback length is the partial match that we found. And what is this partial match though? And where do we find this? And where's this magic match? And where do we find it, right? So it's like the magic animal and where we find it. So to find this one, we need to look at, if you look at this green bit and the red bit, the green bit here is actually the suffix of the target string that we have looked at so far, the end of it. And this red bit is the prefix, the starting point of the pattern string. So if there's a match of the suffix and the prefix, then we have to restart from that point. So the delta here, its definition is the length of the matching suffix of the target string that we have checked so far, and the prefix of the pattern string. So that's 1. Now, can we generalize this a little bit? If we move on, we will find that actually, yes, this is, if we keep moving, right? If we forget about stopping at here, mismatch and all that, if you look at this one, actually, we have a match of 6 letters. And then at this point, we have a mismatch. So how fast do we jump? And again, ideally, we jump from the first mismatch point. But again, we can't jump that so much because, again, there's a bit of green bit that matches with this red bit. So we have to fall back a little bit. fallback to here. Yes?
How does the computer find delta?
Very good question. And again, that's what will happen next. So if there's anything I'm good at, I'm very good at predicting your questions. And the reason for that is I've been doing here for like almost 10 years now. So I can sort of forecast that. But that doesn't mean that you shouldn't ask questions. Please, let's keep a lively lecture. Very happy to take your questions, right? So again, that's the length of this match. Now, keep going. Here, this time, I actually have a 3-letter match of the suffix and the prefix. And without that animation again, we already know that we should move forward this bit. So jump forward the whole thing, but shift back for a delta, which is 3-letter. And the delta is the length of the match of the suffix and prefix. So that's that. Again, let's not worry about how this is calculated so far. And let's just try to sort of keep moving with this algorithm. And first understand how the overall algorithm works, and then we'll come back to look at how to get that. But intuitively, how do we get that? In the most straightforward solution, though, is that now whenever there's a mismatch, you basically just start from the last letter of the target string that we've looked at so far. So we look at a suffix of length 1. Do you have a match with a prefix of length 1? No. And look at suffix of length 2. Do you have a match of prefix length 2? No. Suffix of length 3, prefix length 3, actually there's a match. So we found a match of length 3, but we don't stop there. We have to see, well, let's look at 4 letters. Do we have a match of 4-letter suffix with a 4-letter prefix? No match. 5-letter suffix, 5-letter prefix, no match. And keep doing this. Keep doing, until we found the longest suffix that matches the prefix. This doesn't help. It's actually slower than the previous solution. We have to have a smarter strategy to jump. And we actually do have a smarter strategy to jump, and we'll cover that after this, right? So now, before we can cover how to know how many letters to jump, let's look at 2 special cases. These 2 special cases relate to when there's a mismatch happens in the first or second letter. So here, the first special case is if you have a pattern string and a target string and start doing this match, and if they match in the first letter, but right start from the second letter, there's a mismatch. We don't know what this letter yet, but don't worry about it. Just somehow we know they don't match. Now, we want to have a general solution that says, well, whenever there's a mismatch, I want to jump with the S variable, S iteration variable. And our jumping equation, the governing equation for the jumping is we want to go for S plus I and then fallback a delta. So in this case, I know the mismatch point is at I being 1. So if I follow this equation, we'll do S equals to S plus 1, which means the next time I will start from this bit and we'll find a subsequence to trying to match with the pattern sequence. And that's actually the right starting point, right? If the first one don't match, then most naturally, I'll start from the second one. That's how we move. The first one match, second one don't match, then we have to at least move forward by 1 letter. We can't move any less than that. If we move any less than that, it's a repeated computation, right? But based on our governance equation in here, I have to go for S being S plus 1 and then fall back a little bit. But actually, I don't want to fall back in this case. I really do want to just jump for 1 position. So in this case, I set a special value for delta. If the mismatch appears when I being 1, I'll just force the delta value to be 0. Does that make sense? Essentially, we want to, obviously we can write a lot of if-else statements in our program to test different cases, and in these different special cases, we use a special treatment. But to avoid that, I want to use an overall governing equation, and that governing equation is S being S plus I, the length of matched sub-pattern so far, and then fall back with the delta. In this case, I can't really fall back. I want to just keep going. So in this case, I force delta to be 0. Now there's an even more special case. What if the mismatch happens right from the first letter, right from the beginning? If I start from the right beginning, then again, now I is just being 0, and s plus I is still s. So I'm not jumping forward at all. And that's not great. I have to jump forward. In this case, I set delta to be a special value of a negative value in this case, a special value of -1, such that when s being mismatched, when there's a mismatch, s being s plus 1, s plus I, and I is 0, so s equals to s. Not great, not jumping forward. I have to change the value of x, and to change that, I set delta to be -1, such that we achieve that effectively we say s equals to s plus 1. So another special case. Now, overall, then I have a governing equation to control how s move. When you start from a position for a sort of subsequence match, s actually doesn't move. We just keep moving I until there's a mismatch. When there's a mismatch, s will jump from s to s plus I and then fall back by delta. That's a governing equation to control the movement of s. But what's the governing equation to control the movement of I though? Now, for the movement of I, typically if there's a match, it will just keep going, next letter, less letter, less letter. When there's a mismatch, then there's two possibilities. I is either you set back to 0, you start from the beginning, or it's going for a middle point. And this middle point is the delta value. Like in this case, if there's a mismatch in here, I know I need to move forward and then shift back a little bit. But once I shift back, this subsequence, I don't need to match them again. So I don't need to set back to 0 and restart from this point, but instead, you can start from the delta value in here. So for I, the governing equation is either delta or 0. Which one is greater? When there's a delta value not being non-zero, that means I've got a mismatch, I've jumped forward, and I shift back. But I doesn't need to start back from the beginning. It can also shift forward a little bit. This is where we got the saving. So we don't need to start right from the beginning again every time. All right? So far, so good?
The reason you need a match is delta could just, suppose if there's no match, delta would be 0, right?
Delta could be -1. That's where I...
Deal with a special case of -1 that you need the match.
Exactly. Yeah. So we want to write a single equation for this. But in implementation, you can well just use an if-else statement to do a bit of testing. That's just that, right? So that's the implementation. And let's look at a pseudocode. Again, so far, let's not worry about how to calculate the delta value, just overall governing procedure. So this is KMP algorithm, and this is a description of the algorithm. And we say we can jump forward by s plus I, but we have to shift back a little bit. There's a visualization here, which matches exactly what I just showed you. This is the KMP algorithm implementation. Let's look at how it corresponds to our visualization in here. Can you guys see it large enough? Okay. So this is the description in here. We pretty much like the linear search, so you just keep going. There are two possibilities. One, if you, so we just keep matching the pattern string with the target string. If they match, we'll just keep looking at the second letter in the pattern string, and third letter, and fourth letter, and fifth letter, so on and so forth. We just keep increasing I, but S don't change. So S is pointing to the starting point of a subsequence that we want to use to match with the pattern string. So T here is the target string, P is the pattern string. So we just keep doing it. If we've matched the whole M letters from the pattern string, we'll say that we found a match, and we return S. S here being the starting position of the match subsequence of the target string. Now, if there's a mismatch, the else case is the mismatch case. If there's a mismatch case, by definition, following our governing equation, we say S will jump to S plus I and then fall back. And what's the fallback length? Here we are representing using an array Fi to represent the fallback length and not delta anymore. The reason why we can't use a delta is because the delta can change. Depending on where your mismatch happens, the delta can change. And the where here is representing by the I. So if your mismatch happens at the I's position, the fallback should be Fi. And Fi is actually an array that stores all the different delta values. So that's how we get it. And next we'll talk about how to calculate this F array. And this is actually, on the book, it's called, on the textbook or on the slides, it's called the failure function. But it's not really a function. It's just an array that stores all the different delta values that you want to use them to govern your fallback length when the mismatch happens at different positions. And I, again, based on our governing equation, I is either respect to 0 or it jumped to the delta value. So that's the overall governing process of the KMP algorithm. So far, so good. Great. Now, then next, we're going to try to analyze why does this KMP algorithm give us, a better than n times m kind of complexity. Now, previously, we showed you that if you calculate the delta value in a straightforward way, you have to check whether there's a match of length 1 of the suffix or prefix, length 2 of suffix or prefix, length 3 of suffix to prefix. If we actually do that kind of matching, it's going to blow up the computational complexity. We are not going to do any better than n times m. But the interesting bit here is that actually the delta value somehow magically, someone will give us that. So getting that takes only one time. But even with this process, can we guarantee that we can do better than n times m, or n times n time? Why is it better? Now, to analyze the time complexity of this one, this is a bit more complex though, not as easy as before, but we can start from a simple analysis, all right? Now, suppose, let's not worry about the second half of the else statement. Let's not worry about the else branch. Just look at the if branch. So if we only have this part, this is obviously n times m, right? This is essentially what we have in the previous linear kind of such procedure. Now, if we fall back even a bit more, just think about a simple for loop that loops for a looping variable I that goes from 1 to n. How much time does that take? How many iterations do we need to go from I being 1 to n? N iterations. Very good. Now, if I have two looping variables that both, one looping variable want to go from I to m, one looping variable is I, or maybe s in this case for consistency. I have a looping variable s that wants to go from 1 to n. Again, that's just n iterations. Now, if I have a looping variable I that wants to go from 1 to m, that's m iterations. Now, if both variables, if I have two looping variables now, not one, right? Now I consider two, s and I. And in each iteration, you can do one or two things. You either increase s by 1 or you increase I by 1. Now, in order to make both s and I to reach n and m, how many iterations are there? Two variables, s and I, both starting from 1. Now, in each iteration, you have two options. You either go for s plus 1 or you go for I plus 1. How many iterations do we need for both variables to reach their upper bound n and m? Anyone else? Let's give someone else a try. I know I hear someone says n times n. Do you want to change your answer? Yeah? If you put them into nested loops, that's n times n. But I'm not talking about that. I'm talking about making them into if and else statements. Each iteration, you either go up by 1 for one of the looping variables, n plus m, very good. That's the idea. And here, this is the idea. So in each iteration, if you look at here, there are two branches, right? If you look at here, either I goes up by 1, or the other one, S goes up by something. Here, actually better than goes up by 1. It can goes up by I, except that there's a little bit of fallback. So it looks like we can even, you can derive this n sort of linear time complexity of this KMP algorithm easily. Just looking at the two variables and each iteration, either one of them will go up by 1, but not quite yet. In this case, in the first case, indeed, I goes up by 1. But in the second case, S does not necessarily go up by 1. It could go up by I minus Fi. Now the issue though is that here I could also go up by Fi. So they can actually cancel each other, which means in this iteration, in this first branch, actually I do go up by 1, but in the second branch, it's not like S go up by something, but I stay there. It's like S go up by something, but I goes back. The previous analysis that we say is either S go up by 1 or I go up by 1, then we can guarantee n plus m. But there's an implicit statement that says when S goes up, I don't change, right? But here, I can change and can go back to 0. So that doesn't work yet. And actually, to make the analysis work, here we need to introduce another one. We say, well, let's not analyze S plus I. Let's analyze 2 times S plus I. And the reason why we want to analyze 2S plus I is that, well, you said I can fall back a little bit, and X can go forward. And the bit that S goes forward and the I that goes backward, they cancel out each other. But what if I consider 2 times X? So 2 times X is like going forward this and going forward like this. Even you have an I that goes backward for a bit, I still have something that goes forward in each iteration. So that's the analysis where we are doing here. But obviously, if you consider 2S plus I, then what does the time complexity give you then? What would be the upper bound then? So if you look at S, the upper bound is n. So if you look at 2S, what's the upper bound? 2n, right? So then the overall time complexity becomes 2n plus m. Not n plus m anymore, but still very good because we know for big O analysis, constants don't matter. So the 2 just got thrown away and we got n plus m kind of time. So here, that's the intuition how we derive the time complexity. Here is actually the detailed step of the derivation. There are actually 3 different cases, as we just showed you. The first case is just that if there's a match, which is the if statement in here, if there's a match between the, here the analysis is that let's look at iteration k, what's the status of I and S? And then we look at iteration k plus 1, the next iteration, how does S and I change? And I'm going to show you that after one iteration, 2 times S plus I will go forward by at least 1. And that's how we guarantee that after 2n plus m iterations, 2s plus I will hit the respective upper bound, right? So that's the analysis. So here, the actual value of I and S at iteration k doesn't matter. What matters is the difference between iteration k and k plus I. What's the value difference between the sum of these 2 variables? Now, if there's a match, the if statement here says that let's increase I by 1, and S, let's not worry about it. We don't change S, right? So after one iteration, if there's a match, the increment of 2S plus I is 1. We have that, right? So far, so good. Now, what if there's a mismatch? When there's a mismatch, there are 2 possibilities. If the mismatch happens in the 0th position, the first letter, they don't match. If the first letter, they don't match, by definition, well, if the first letter, so now it's the iteration k, if at iteration k, the first letter don't match, then I don't change. It starts as still first letter of the pattern string, right? First letter doesn't match, I can't move on. And by definition, if there's a mismatch, S needs to move up by I and then shift that by delta. Now, we know this Fi value. We know when there's a mismatch, S must move forward. It will at least move forward by 1. That's the analysis that we showing previously, right? If there's a mismatch that appears at this position already, S must move up by 1. So here, in this mismatch of the first letter, S will become S plus 1, move to the next letter. And if you do 2S plus I, then actually 2S plus I would be 2S plus 2 because S is now S plus 1. So the gap, the value gap between the sum of 2Si in the 2 iterations is 2. So basically what I'm just doing is just to subtract 2S plus 2 by 2S. We got a 2. Now, in the last case, still a mismatch, but this time I have a mismatch at the position of a certain value where I is greater than 0. So there's a delta value that's a mismatch in there, right? And if there's a mismatch in there, this is the second case, well, the third case. The last case is I sort of stay at 0. Another case is I will move forward at a delta. So I now is at delta because there's a mismatch, but there's something that got matched. There's something got matched, I will stay there. It doesn't need to go back and look at it again. So I got moved forward and it's now at this delta value. And by definition of the calculation, S is calculated by S plus I minus delta. And if we add them up, now this is the key bit. If we just add up these two values, the Fi got canceled out. They don't work. So that's the reason. This is the key bit where we have to do 2S rather than just 1S. If we just do 1S, S plus I, they cancel out the Fi. It's not great. So I'll do 2S plus I, and by definition, S is this value. 2S would be 2S plus 2I minus 2Fi. And add up with Fi, I'll get 2S plus 2I minus Fi. Now, the difference between these two equations now is I minus Fi. And it's guaranteed that I minus Fi is greater than 0. Right? Why is I minus Fi must be greater than 0? Because there's a mismatch at position I. And the delta value can be as long as whatever that is mismatched. So if you have a mismatch at position 4, the delta value at best can be 3. So delta is guaranteed to be smaller than I. So I got, again, a guarantee of increment of at least 1. So in each iteration, if you add up 2S plus I, they must got increased by at least 1. So after 2m plus m iterations, will be done. And that's a linear search kind of sequence. So far, so good? If so, let's take a quick 10 minutes break. After that, we'll come back to look at how the delta value is calculated. And after that, we'll move to the test. Right? We will take 10 minutes break, come back at 11. Okay, let's get the delta value calculated, and then we're done. All right? So how do we calculate the delta value? By definition, to calculate the delta value, we want to figure out when there's a mismatch, how long a prefix of the pattern string matches a suffix of the mismatched target string. And as we just said, what we can do is we can do an exhaustive search. We can calculate, all right, do we have a one character match? Do we have a 2 character match, 3 character match, and so on and so forth, up to do we have an I letter match? That's one way to do it, but that's not super efficient. And also, it's relying on at every position of, at every sort of mismatch of the target string, we have to recalculate once. And that's not great. But actually, we can pre-calculate that process. Why can we pre-calculate this process? Like here, we say when there's a mismatch, we need to know what's the delta value, and we calculate this delta value in the current version of the algorithm. We calculate this delta value whenever we need it. but actually we don't have to calculate it whenever we need it. And actually in this pseudocode that we show, we actually don't calculate it. Instead, we just fetch it from somewhere, an array that stores these delta values. But why can we pre-calculate them? We know the delta value is a match of the prefix and suffix. And the suffix, we say, it comes from the target string. And the prefix comes from the pattern string. How can we calculate it without looking at the target string? Yeah? Yes?
Is it because the pattern string is always going to be shorter, so it's always just going to be like the length of the pattern string?
Pattern string could be shorter, good observation, but still it doesn't answer the question, why can we pre-calculate it without looking at the target string? Delta is a match between a prefix of the pattern string and suffix of target string, right? So we are talking about suffix from the target string, but we can actually calculate it without looking at the target string. Magic. Now, can you see? If you look at the yellow bit, the highlighted section in here, what do you see? Or maybe if I change the color of here, now what do you see?
So the target string is the big string we're searching through?
Yeah? Yeah. And we are saying that we can calculate delta value without looking at the target string. Yes?
Because you can process the pattern string before you go into the target string. And in this pattern, you can see that it's got a she, and after this was in the pattern string, and then it goes to a star and then another she. So which means when I is larger than 4 and less than less than 7, and in this pattern, your delta should be -4.
Very close, very close. Yes?
Is the answer that like you don't need to look at the target string because we have pattern, we know I, which is how long the previous substring match was before we found a character which was breakage. So we already know something about the target string because there was that first match.
Exactly. So even though we say we are trying to find a prefix of this pattern string and a suffix of the target string, the issue here is though when there's a mismatch, anything in front they actually match. And when we say match, we mean they are the same. So if you want to find a suffix from the target string match that matches the prefix of the pattern string, you just look at the suffix of the pattern string. That's all that you need to do. That's the magic. So we can pre-calculate this delta value by just looking at the pattern string. And you are absolutely right. The pattern string usually is a bit shorter. So if you just process the pattern string and using, again, a little bit of black magic, we can show that you only need a linear time, just one sequential scan of the pattern string, you can calculate the delta value. So that, again, only adds a linear cost. Previously, we established that KMP takes n plus n time, well, 2n plus n time, but still a linear cost. And then now you add another n to it, still a linear cost. Yeah, you got a question?
So I guess my question before we started talking about delta was the algorithm is looking from the start. So it's like, oh, S matches, H matches, E matches, great. But why are we doing it from the start of the pattern string? Because in the case where we find that it doesn't match, then we can only skip forward by a certain amount. Whereas if we start checking from the end of the pattern string, so like for example in this one, if we looked at the S at the end of seashells and we found out that doesn't match, then we know that we can skip all the way ahead, right? So although it may be that we get that partial match, it could just as easily be that we get like I don't know, V shells, right? And we only find out once we get all the way to the start. On average, it should be faster because on average, it will allow us to skip faster. So why don't we count backwards from the end of the pattern string?
Fantastic observation. That's our next algorithm called BMH. But unfortunately, we don't have enough time to cover that. This is for your own reading only. The idea is very similar to KMP, but it starts from the right. Very good observation. And actually, this is the sort of more practical implementation of the algorithm. So in practical systems, this BMH algorithm use a bit more than the KMP algorithm. But the idea is very similar, and we recover a sort of similar and, in our sense, a bit more intuitive solution. That's just that, all right? But very good observation. Coming back to delta calculation, any other question about delta? I know Shannon warned me that the class is very interactive, and I should reserve more time for questions. And hopefully we will got enough time to finish delta calculation. Yes?
So for this example, what would the array of delta be?
Very good. We will give you a sneak peek. The array of delta value will look like here, this bit. I have hidden something such that I can show you step by step how this is calculated, but I can sort of give you a sneak peek. The array looks like this, but we will derive step by step how this value is calculated. But exchange is just an array of integers. Okay. Now we established that to calculate the delta value, we only need to look at, by the way, delta value again, in the textbook or many other places, you see it as a failure function, but it's just a value of an array that stores all the delta values, right? Now, we established that the delta value can be pre-computed by only looking at the pattern string once. Now, how do we do that though? Now, we didn't establish that we can do it by looking at it just once. We only established that we only need to look at the pattern string. How many times we don't know yet? Next, we are going to establish that it will only need to be looked at once. But why is it once? Now, to understand that, we need to kind of go back to this very simple example. So in here, we found a mismatch. We found a match of prefix and suffix of length 1. Now, if we take a further step, if I know now this mismatch is in here, do we need to go all the way back to check whether there's match of prefix or suffix? We don't, because we know there's a match of S. If we want to find further match of prefix and suffix, we just start from S and look at whether there's a letter of H that match. From the same logic, if there's a match, we look at whether there's a two-length match already, and we're looking at the third. We don't start from all the way back, but we just continue from where we left from last. And that's the idea of how to just look at it once and get it done to build up this delta array. And next, I'm going to show you. That's the idea. We progressively build it up by reusing previously calculated delta value. That's the core idea. And here, the delta value array, we call it an array of F to just be consistent with the textbook on the slides, failure function array, right? So this is delta value. And we established that if the mismatch happens in the 0th position, we need to jump forward by 1. And the delta value is -1. This is just a special case that we always impose it, right? This is this special case we're showing here. If the mismatch happens in the first position, the 0th position, the delta value should be -1. So that's the reason why we kind of hard-code the first one, -1. And the second one, now it's all pattern string, no target string anymore. Don't worry about the target string. And the second one, if the mismatch happens in the second letter, we hard-code it as 0. So this is our two special cases that we just covered, right? In the last lecture, well, in the first hour of the lecture. Mismatch at the first position, jump forward by 1. So delta is -1. If there's a mismatch at the second letter, jump forward by also 1. But because I is now 1, delta doesn't need to be 1 anymore. Delta can be just 0. So this is just corresponding to the two special cases that we analyzed in the first hour. Next, the calculation really happens starting from the third letter. And remember, we use two looping variable. S here represents the mismatch position. So now I have a mismatch at this letter. And I want to figure out if I had got a pattern mismatch at here, how much I can jump forward. And this is the place where we start calculating, well, let's look at a suffix of this So this is the point where there's a mismatch. And this will be the segment where we look at the prefix and suffix and see whether there's a match or not. And C here is a sort of looping variable to keep track of how long this prefix got matched by a suffix. Okay? Mismatch position, length of prefix, and obviously we need to try to match this prefix with a suffix. And apparently this one and that one don't match. So if they don't match, apparently the delta value should stay at 0, right? And we got a delta value of 0. What's the governing equation though? Let's look at. These examples are just exactly the same as I showed, so I won't repeat it. But I will show you together with the code. And the code, if you look at here, it looks actually very similar to the KMP algorithm itself. The calculation of failure function, again, has a looping variable that loops through the whole pattern string, just like previously, we have a looping variable that loops through, and so this is KMP, and we're going through all the characters in the target string. Now we are just going through all the characters in the pattern string. Just going through that. And this initialization in here is just what I show you. I hard-coded the first letter in the failure function is -1, second one is just 0, and then starting from this third letter. So if I have a mismatch in here, what should be the value? And C here is the length of the prefix that got a match. And this match of the prefix will be progressively grow. At the moment, there's no match, so this value is just 0. This is the branch. So if there's a no match, I'll just set this. So here it's actually setting two values in one statement. This basically says let's set fs to be 0 and let's increase s by 1. So there's a mismatch, and I'm just testing. This is the prefix. This is the prefix bit. PC is the prefix bit, and ps minus 1 is the suffix bit. Because S here is S here is the mismatch point, and S minus 1 is the prefix, is the suffix of this match segment, right? So looking at the prefix and the suffix. Prefix is looking at the C position, suffix is looking at the S minus 1 position, and apparently they don't match. And according to this governing equation, if they don't match, let's just set the failure function value to be 0, and let's move on. And again, I'm going to look at, is there a match with the prefix and the suffix? No match. So this would be, again, 0. Keep going. Is there a match with the suffix and the prefix? No match, right? So this would be, again, 0. So far, so good. We've covered one of the branches. Next, I'm going to cover the second branch. And this third branch is very special. We'll cover it at the last, and let's not worry about it so far. So now we are looking at, this is actually the second branch, where there's actually a match of the prefix and the suffix. And the match is a length of 1, right? So if there's a match, then I'm going to increase C by 1 because there's a match. So we increase this one such that later on, as you can see, if we keep moving, I can maintain a prefix of length 2 that matches the suffix of length 2. That's the reason why I want to increase this length of prefix. Once I increase that by 1, this S can move on to the next one. And also, the failure function is calculated as C plus 1. The reason why we need to do C plus 1 is because this C plus 1, the C plus 1 calculation is done before C is increased by 1. So when we do this failure function calculation, when we update this element, C is still at here. So that's the reason why we say Fs equals to C plus 1. So because we are writing everything in one single statement, we probably shouldn't do that. If we write it in separate statements, it's a bit more obvious. But anyway, the idea is just that the failure function is trying to keep track of how long a prefix, which is tracked by C, matches a suffix, which is tracked by S. So far, so good. So this is second branch. And if we keep going, now we are looking at the mismatch at this point. And again, I'm going to compare this letter with the letter currently pointed to by C. So that's the beauty about this progressively building up the array. We never need to look back and trying to see, well, do we have a match? 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 We know that we don't have a match by building up, looking at all the previous characters already. If there's a match, I will have checked that before. So all that I need to do in each iteration, I'm just comparing with the letter that is immediately before the mismatch point with the prefix point, which is pointing to by the variable C. And this is the way why we just need to go for one iteration and get it done. All right? So far, so good. Now, in this case, if I have a mismatch point in here, I'll just, following the previous procedure in here, I'm just comparing the letter right before the mismatch point with the letter pointing to by C. And again, there's a match. And by the calculation, it says, if there's a match, I'm going to set fx to be C plus 1. C now is 1, so C plus 1 would be 2. So this would be 2, and then I'm going to move forward. And then I'm going to move forward. Now, so following the same procedure, I'm going to now look at a mismatch point in here. So tell me, what would be the value in here then? Very good, 3, right? And the reason why we have a 3 is because now this letter E, right before the mismatch point, matches the letter that matches pointing to by C. There's a match, and our rule says if there's a match, let's set this failure function value to be C value plus 1, which is C value is now 2, so make it 3. Now, we are looking at the mismatch point at here. What should we say though? And again, by these rules, we say we need to compare the letter right before the mismatch point with the letter pointing to by C, and they don't match. When they don't match, don't worry about the middle branch. When they don't match, just look at the last branch. When they don't match, we want to restart. They don't match, so there's no match between, with this suffix and the prefix. So I have to restart the prefix right from the beginning. So restart, and this will set it to be 0. And obviously, the last one will also be 0 because there's, again, no match. Right? Because this letter wouldn't, the letter right before the mismatch point won't match the prefix point pointed to by C. So they don't match, this will also be 0. So far, so good. So in this demonstration so far, we only look at 2 of the branches because the last branch is here is the most challenging bit of the whole KMP algorithm. So I save it with a second example. But before I move on to that, I want to make sure that these 2 relatively not so complex bits are sort of covered. Do you have any questions about what we covered so far? Essentially, we progressively match a suffix of the mismatch point with a prefix. We progressively build that up, right? Now, when there's a mismatch, and when there's mismatch and even a mismatch with the prefix and suffix, previously we say we start back right from the beginning, but actually not quite so. And next, I'm going to give an example why we probably shouldn't just restart from the right beginning. And here is an example. Now, suppose now we are looking at a mismatch point at here. And apparently, if you look at a mismatch point at here, according to the algorithm, again, I'm going to compare this suffix character with the character pointing to by the previous character pointing by C. And apparently, E matches E, right? They do match. So by our rule, we're going to, again, set this failure function value to be C plus 1, which will make it 3. And indeed, it's 3. And you might be wondering, why am I doing this? This seems to be exactly the same as before. Now, the magic happens in the next letter. according to the rules, right, we set the failure function value at here by c plus 1, and we increase c by 1, and then we increase s by 1. Now next, we are considering a mismatch point at here. When there's a mismatch point at here, again, following the rules, we compare L with the star, and they don't match. When they don't match, previously we say when this prefix point and the suffix point don't match, we should start from right beginning. But in this example, we shouldn't. And to show you why we shouldn't, I'm going to give you a target string. So this is target string, and I have a pattern string, and the pattern string is just exactly a duplication of this pattern string here. Now, I have found a mismatch at this point. Previously, we say when there's a mismatch point at here, I should set this back to 0. And if we do set this back to 0, that means I can jump all the way through. Right? Previously, we say when this one matches this one, I'm going to set this value to be the value of c by 1. And if they don't match by this else branch, I'm going to set failure function value to be 0, which means delta is 0. And when delta is 0, I'm going to go all the way to the front, and I don't fall back. And if I go all the way to the front and I don't fall back, I'm going to end up with a situation like this. Right? So this is the mismatch point. This is the mismatch point, okay? And we don't fall back. And if we don't fall back, we'll end up with a comparison with like this. But if we do this, did we miss something? If I look at this string, actually there's a match. But somehow we missed that. Now, KMP is fast, but what did Shannon say in his last lecture? You can have a fast algorithm, but before an algorithm is make it fast, it has to be correct, right? We got a fast solution, but it's not correct. So when the mismatch point is at this point, we can't go all the way back to 0. We have to go back a little bit. And this little bit is actually at this point. And if we shift back by 2, they could match. But why should we move back 2? How do we know that should be 2? Well, actually, if you look at this bit, there's actually a little bit of prefix that match a suffix of it. So now it's really the mind-blowing bit. We are finding a match with a prefix and a suffix. But when there's a mismatch of the suffix, I want to find a prefix of this suffix that match of the suffix of this suffix. And that's the bit where we want to shift back. How do we know what's the length of a prefix that match of the length of a suffix of a suffix? We don't know that, right? But luckily, if you just look at this part, this part is just a cut. This is just a cut of this prefix in here. This is just a cut of that. And we know that this is the mismatch point. The star and L don't match. This is the mismatch point. When there's a mismatch point, I want to find a prefix that matches the suffix of this prefix. What's the length of that match? We have been talking about how to calculate the delta value, right? And the delta value is just the length of a prefix that matches a suffix, right? So we actually have already calculated the failure function value at this point. And so if there's a mismatch at this point, I want to find a prefix of this prefix that matches of a suffix of this prefix. What do? We just take the failure function value. That's the length. And that's what's happening in here. This is the mismatch point. And before, this is the mismatch point. And I know its previous letter doesn't match the last letter of the prefix. But that doesn't say that there can't be some some letter in this prefix of this suffix that match of a suffix of this suffix. And how much there's a match, and there's a match, that the length of that match can be calculated by just the failure function value pointed to by C. And that's just this value. And that's the idea. And in fact, this is set to be 1. Oh, actually 2. This is value of C now has a value of 3, and F3 is actually C got reset back to FC. So C is this value, and FC, what is FC? FC is 1. FC is 1, so I've got set it back in here. When it sets back to here, again, I'm going to compare L with this letter L. And when L matches L, we will calculate this one, which gives you a value of 2, because now L matches L, and when L matches L, the rule says that Fs should be C plus 1, and C is 1, so 1 plus 1 is 2. That's the idea. Very complex, and I can see that very confused. But any question that I might be able to try to answer? Perhaps not. Let's not to worry exactly what's happening, and you can analyze this process after class. So the important thing is just understand the process. When there's a mismatch point at here, when we will look at the ending of the prefix, which is pointed to by C, and the letter just before the mismatch point. And if this point and that point doesn't match, we don't start right from the beginning again. Instead, I want to check if there's a little bit of prefix that could match a suffix of this suffix. And again, we reuse the previous principle. We know this bit and this bit don't match, but I know that the front few letters of them matches. So I'll just examine this substring in the front and see where there's a little bit of prefix that match a suffix of this prefix string. And to get that, we use this delta value that we have previously calculated. We basically just reuse the delta value at here, and we reset the C value and restart the comparison from there. And with that, I'll stop.